Good morning. In today's session, we are going to discuss about tunneling barrier, specific contact resistance, heterojunction materials, energy band diagrams, etc. Okay. Now let us discuss about tunneling barrier. We know that the depletion region width or the space charge width in a metal semiconductor contact or ohmic contact is inversely proportional to square root of semiconductor doping. Now, as we already studied, the width of depletion region decreases as doping increases. This as doping concentration increases, the chances of tunneling, that is crossing through the barrier, also increase. This is figure shows a junction in which metal is in contact with a heavily doped n-type epitaxial layer. Now here, if you want, you can skip that diagram. No need of drawing. Instead, you can directly write the expression for tunneling current. Okay, as given by this equation, and you can write this sentence also. The tunneling current increases exponentially with doping current. Okay, that is how tunneling current increases. That is an exponential increase with doping concentration. Now we are going to learn specific contact resistance. A figure of merit of ohmic contact is called specific contact resistance. It is denoted by RC. It is defined as reciprocal of derivative of current density with respect to voltage evaluated at zero base. So here you get a definition and its corresponding expression. Its unit is ohm centimeter square. Now for ohmic contact we need this RC, that is the specific contact resistance, to be as small as possible. Okay. For a rectifying contact with a low to moderate doping concentration, this is how the voltage current relation or current voltage relation looks like. In this junction, the dominant factor is that of thermionic emission. In such case, that is in the case of low to moderate semiconductor doping concentration, the expression for specific contact resistance is given by this. Now the specific contact resistance decreases as barrier height decreases. This is how specific contact resistance varies with barrier height. As barrier height decreases, specific contact resistance also decreases. Now for a metal semiconductor junction with high impurity doping concentration, the tunneling process will dominate. That is, the crossing across the barrier will dominate. That is, it will take place frequently. In such cases, the expression for specific contact resistance is like this. This means that specific contact resistance is very strong function of semiconductor doping. So we have seen the expression for semiconductor, the expression for specific contact resistance in almost three cases. In the case of heavily doping, in the case of when high impurity concentration increases, etc. For doping concentration greater than 10 raised to 19 centimeter per cube, tunneling process dominate and the specific contact resistance, that is RC, will show an exponential dependence on doping concentration ND. Now for low doping concentration, the value of specific contact resistance depends on barrier height and becomes independent of doping. So the above equation that we have discussed corresponds to a metal N plus contact. Whenever you see an N plus, that means it is a heavily doped N type semiconductor. The plus sign indicates heavily doped. Okay. However, if you are making such a junction like N plus N, that is a heavily doped N type semiconductor with a moderately doped N type semiconductor, then also specific contact resistance will have this type of variation. Okay. Now for a fairly low doped N region, the specific contact resistance will dominate total resistance of the junction. Now in order to form a good ohmic contact, we have to create a low barrier and we have to use a highly doped semiconductor at the surface. However, in the actual technology of fabricating good reliable ohmic contact is not very easy, and it is very difficult to fabricate such a good ohmic contact on a wide band gap material. That is, wide band gap means materials having high energy band gap. Okay. Generally, low barriers are not possible on these wide band gap materials. So a heavily doped semiconductor at the surface have to be used in order to form a tunneling contact. Also non-uniformities, that is inhomogeneity in the surface doping concentration, will also prevent the theoretical limit of specific contact resistance from being reached. So in order to achieve a good ohmic contact, it is not practically, it's not possible to achieve a good specific contact resistance due to the above discussed difficulties. Okay. So up to this slide, they are discussing about what is meant by specific contact resistance and their variations according to doping concentration. Okay, and the corresponding expressions. Next is heterojunction. When two different semiconductor materials are used to form a junction, we call it as a semiconductor heterojunction. And if you are using same semiconductors to form junction, then you call it as a semiconductor homojunction. Now let us see what are the heterojunction materials. As already discussed, in order to form a heterojunction, we use two different materials having different energy band gap, and there will be a discontinuity at the junction because we are using two different semiconductors with different band gaps. So definitely there will be a discontinuity when you look at the junction. Okay. That is, we have an abrupt junction in which the semiconductor changes abruptly from a narrow band gap material to a wide band gap material, because you are using two different materials with different band gaps. So definitely there will be a disruption in their band gap at the junction. Then okay, now next one is they are given an example that you need not study. In order to have a useful heterojunction, what you have to do is that the lattice constant of the two materials has to be well matched. That is the first criteria that has to be satisfied when you are making a heterojunction. That is, lattice constant of the two materials that you are using must be well matched. So lattice match is very important, because if there is any lattice mismatch, that will introduce dislocations, that means discontinuities, and that will result in interface states. So you will not be able to form a good heterojunction. Okay, so lattice matching is a must if you want to make a good heterojunction. Now these are the energy band diagrams. In the formation of a heterojunction with narrow band gap material and a wide band gap material, the alignment of band gap energy is important in determining the characteristic of the junction. Now figure A, you can see that shows the case when forbidden band gap of wide band gap material overlaps with the band gap of narrow band gap material. Now that type of overlapping, that is called straddling. Okay, and that is applicable to heterojunctions. Now we consider only this case here. Now the other possibilities are called staggered and broken band gap, and they are shown in figure B and C respectively. So when you are asked to define what is meant by straddling, staggered and broken band gap, you just mention them and draw this figure. Okay, so their concept will be clear. Now here the figure shows energy band diagram of an isolated n-type and p-type material with vacuum level as the reference. Here the electron affinity of the wide band gap material is less than that of the narrow band gap material. That is, you are making a heterojunction between a wide band gap material and a narrow band gap material. That is, there is an energy band gap difference. So here the electron affinity of wide band gap material is less when compared with the narrow band gap material. This difference between the two conduction band energies is denoted as delta EC, and the difference between the two valence band energies is denoted as delta EV. So from figure you can see that delta EC is equal to E into chi n minus chi p. Chi is actually electron affinity, and delta EC plus delta EV, their sum will be equal to energy band gap of p-type semiconductor minus energy band gap of n-type semiconductor, that is denoted as delta Eg. In an ideal heterojunction using a non-degenerately doped semiconductor, vacuum level is parallel to both conduction band and valence band. If the vacuum level is continuous, then delta Ec and delta dV discontinuities will exist at the heterojunction interface. These are a few characteristics. So study those portions that are underlined. If you want, you can draw this figure also. Now this ideal situation is known as electron affinity rule. So if they are asked a question like what is electron affinity rule, then you have to mention this slide along with this figure. Then right up to this much, this is called electron affinity rule. Then the last session, it shows the figure shows an ideal NP heterojunction in thermal equilibrium. For the Fermi level of the two materials, in order to get it aligned, electrons in the narrow bandgap N region and holes from wide bandgap P region has to flow across the junction. Okay, that is, we know. As in the case of homojunction, this flow of charge carriers will create a depletion region. This depletion region's width into the N region is denoted by Xn, and the depletion region width into the P region is denoted by Xp. Okay, so when you are forming a junction between a narrow band gap N-type material and a wide band gap P material, electrons will cross across the junction and you will get a depletion region, and a part of that depletion region, that is a small portion of the width of that depletion region thus created, will be extended towards N region, and some part of it will extend towards P region. Now that part which extends towards N region is represented by Xn, and that part which extends towards P region is represented by Xp. The discontinuities in the conduction and valence band and the change in vacuum level are shown in this figure. So here you need not draw the figure, you just write the paragraph, that is enough. Okay. Okay, that's it for now. Thank you.